There was a time when a particle of light could not travel very far. It might begin its journey in the young universe, but almost immediately it would be turned aside. Around it was a hot, crowded sea of charged particles, restless and dense, where every direction led into another encounter. Light existed everywhere, but distance had not yet become open space. There was brightness, but no clear view. This is one of the strangest beginnings in cosmic history. The universe was not waiting for light to appear because light was already there. What it was waiting for was the possibility of seeing. A beam needed room to cross. A signal needed a path. The cosmos had to cool enough for matter to settle, for the fog to thin, for radiation to stop being trapped inside its own beginning. Only then did an ancient glow escape. That glow still surrounds us now, stretched by time, until it has become almost unimaginably faint. It is not the light of stars and not the light of galaxies. It is older than both, a quiet remnant from the moment the universe first became transparent enough to let something pass through. But after that first escape, the sky did not fill with stars. There was still a long darkness ahead, a darkness where gravity worked silently, drawing gas into hidden places, preparing the first true fires. The first dawn of the universe was not a sunrise in any familiar sense. It was a slow change in what light was allowed to do. So, the question is not simply when light began. The deeper question is when the universe became a place where light could travel, reveal, and finally be read. There was a time when light could move but could not yet make a journey. In the young universe, a particle of light might begin to travel, but almost immediately it would be turned aside. Around it was a hot, crowded sea of charged particles, moving with such energy that no clear path could remain open for long. Light existed everywhere, but it could not yet cross space in the way light does now. It could not leave one place and arrive somewhere else with a memory of its origin. This is the first strange condition we have to enter. The early universe was not dark. It was filled with radiation, heat, motion, and collision. But it was also opaque because light was trapped in constant contact with matter. It could not carry a clean message from one region to another, or reveal an edge, a distance, or a horizon. There was brightness, but no view. That difference is easy to miss because in ordinary life, we almost always connect light with seeing. A lamp turns on, and a room appears. A window opens, and the outside world takes shape. Light for us is the thing that brings the hidden world forward. But the early universe reminds us that light alone is not enough. For visibility to exist, light must travel freely enough to preserve information crossing distance, without being scattered so often that its story is erased. In the first ages of the cosmos, that simple journey was not possible. The universe was filled with plasma, a state of matter in which electrons had not settled into atoms but moved freely among atomic nuclei. These free electrons were the great obstacle. They scattered photons again and again, changing their directions before they could travel far. A photon did not stream across the cosmos like a beam crossing a quiet room. It wandered through web interruption. So, the first problem in the story of light was not absence. It was entanglement. Matter and radiation were still bound together in a dense, restless mixture, and every part of the universe was participating in the same blinding fog. This was not a fog of water droplets, like the kind that hides a road or softens the edge of a field. It was a fog of interaction, where charged particles kept light from becoming a messenger. If there had been an eye inside that early universe, there would have been no sky for it to read. Light would have arrived from every direction, scattered and rescattered, with no clear origin. There would be no stars, no outlines, no depth, no distant glow separated from a nearer one. The world would not be dark, but it would still be invisible. The difficulty was not that light was missing, but that light could not yet form a relationship between source distance and observer. This gives cosmic dawn a shape very different from the one we might first imagine. It was not simply a story of light entering darkness. At the beginning, light was already present. What had not yet appeared was transparency, the open condition that allows light to cross distance and become evidence. The young cosmos had to change before it could be seen, and that change would come not through a new source of brightness, but through a transformation in matter itself. In those early ages, the universe was expanding from a far hotter and denser state. Expansion did not mean that matter was flying into an empty space around it. It meant that space itself was stretching, carrying matter and radiation with it, lowering the temperature as the cosmos grew larger. The change was slow by human feeling, but profound in physical consequence. Every increase in scale made the young universe a little less dense, a little cooler, and a little closer to the conditions in which light could finally travel. As long as the universe remained too hot, electrons could not remain peacefully attached to nuclei. The simplest atom, hydrogen, requires an electron bound to a proton. But in that early heat, any fragile attempt at stability could be undone by energetic radiation. Matter stayed ionized, broken into charged pieces, and those charged pieces kept the fog in place. This is why the early universe could be full of light and still leave no image behind. Photons were not absent. They were everywhere, but they were too often scattered to build a picture of anything beyond their immediate surroundings. And yet within this unreadable brightness, the future was already being prepared. The early universe was not perfectly smooth. Across that glowing plasma were tiny differences in density, small variations from one region to another. Some places held just a little more matter than average. Other places held just a little less. These differences were incredibly faint, but they mattered because gravity is patient. A region with slightly more matter pulls a little more strongly. Over immense stretches of time, that slight excess can gather more material around itself. What begins as a nearly invisible variation can become a seed of structure. Much later, such seeds would help guide matter into the first great cosmic arrangements: dark matter halos, gas clouds, stars, and galaxies. In the beginning, they were not shining objects. They were only the first quiet preferences written into the distribution of matter. This is one of the most important ideas in the opening of the story. Before the universe became visible, it was already becoming different from place to place. Before there were galaxies, the conditions that would allow galaxies were being written into the cosmic fabric. Before there were stars, gravity already had the first slight preferences it would later follow. The cosmos was not yet a landscape, but it was no longer nothing. It was a glowing, opaque sea with the faintest hidden instructions for future structure. For a long time, however, opacity remained the dominant fact. The universe did not yet have the calm separation that later makes vision possible. Matter was not arranged into stars and worlds. Light was not streaming through dark space between luminous objects. Everything was closer, hotter, denser, and more intimately mixed than the universe we know. The ingredients of later structure were present, but they could not yet show themselves. This is where our imagination has to move carefully. We should not picture a black emptiness waiting for a first spark. We should picture something stranger, a universe so filled with radiation that light itself could not become a clean signal. The first great change would not be the creation of light, but the opening of a path. The cosmos did not need to become bright. It needed to become clear. That path would come through cooling. Cooling sounds almost too gentle for a transformation of this scale, but in the history of the early universe, it is one of the decisive forces. As space expanded, the temperature continued to fall. The collisions did not stop all at once, and the charged sea did not disappear suddenly, but the balance of the universe began to shift. Conditions that had once kept matter broken apart slowly weakened. There came a time when electrons could begin to stay with nuclei. Neutral atoms could form and remain intact. As more electrons became bound into atoms, fewer free electrons remained to scatter photons so relentlessly. The fog began to thin, not as a visible mist might thin at sunrise, but as a deep change in the relationship between matter and radiation. Light was approaching a threshold that would alter the universe forever. For a photon, this meant that a journey was becoming possible. A particle of light that once would have been scattered almost immediately could begin to move farther. Paths that had been constantly interrupted were becoming longer. The cosmos was preparing to let radiation separate from matter and travel across expanding space. The universe was still bright and opaque, but the conditions that held light captive were weakening. There was no witness to this change. No planet waited in the dark. No eye opened. No telescope recorded the moment as it happened. Yet the transition mattered because it would create the first great evidence the universe ever left behind, a glow from the time when light finally began to travel freely. That glow belongs to the next part of the story, but its possibility begins here, inside a universe almost ready to release what it had been holding. For now, what matters is the paradox that comes before it. The first chapter of Cosmic Light is not a sunrise. It is not the sudden appearance of a star. It is a universe filled with radiation, but unable to reveal itself. It is brightness without distance motion, without message light before visibility. Only when the fog thins can light become a traveler, and once it does, the universe will leave behind a signal so old that it comes from before any star ever burned. For hundreds of thousands of years, the universe had been bright but closed. Light was everywhere, moving through a hot plasma where free electrons turned photons aside again and again, so often that no clear image could cross space. The young cosmos was not waiting for light to be created. It was waiting for the conditions that would let light stop being trapped. Those conditions arrived slowly through expansion, cooling, and the settling of matter into a new state. As the universe expanded, its temperature kept falling, and the charged particles that once moved too violently to settle began to lose some of that restless energy. Electrons, which had long moved freely through the plasma, could finally remain attached to atomic nuclei. The simplest atoms began to hold together hydrogen-helium, and the first neutral matter of a universe becoming less opaque than it had ever been. This did not create the later richness of stars, planets, or complex chemistry, but it changed the relationship between matter and radiation. The cosmos was no longer the same blinding sea of free charges. This shift is often called recombination, though the word sounds far smaller than the event itself. It was not a small chemical change inside an existing world, because there were no worlds yet, no stars, no planets, no familiar landscape in which chemistry could quietly unfold. It was a transformation in the whole visible condition of the cosmos. As more electrons became bound inside atoms, the charged fog that had scattered light began to thin, and photons that once would have been interrupted almost immediately could begin to travel. For the first time, light could make a long journey. This did not happen as a flash from one place. There was no single lamp, no first star, no bright point, opening in the dark. The glow came from everywhere at once because the entire universe was passing through the same great threshold. Across space itself, radiation and matter were beginning to part, company and photons were carrying away the imprint of the universe, as it was at the moment they last scattered. That ancient release is the oldest light we can still observe. We call it the cosmic microwave background, a name so quiet and technical that it can almost hide the wonder of what it means. It is not starlight, not galaxy light, and not the glow of any object floating somewhere far away. It is the cooled remnant of the early universe becoming transparent, a faint radiation that still fills the cosmos in every direction. It is a record from a time before the night sky had any stars, before galaxies became islands of light, before the ordinary sources of brightness had appeared. If human eyes could see microwaves, the night would not look completely black between the stars. It would carry a dim background presence, a soft afterglow from a time before there were suns. Not bright in the ordinary sense, not shaped into constellations, but everywhere at once. It would be like seeing the memory of the universe's first clear moment spread across the whole sky. The darkness between stars would have a hidden background, a cooled trace of the first great release. At the time this light escaped, it was not cold and faint. The universe was still thousands of degrees warm enough that the glow belonged to a much hotter range of radiation than the microwaves we detect now. But space did not remain still around it. While the photons traveled, the universe continued to expand, and that expansion stretched their wavelengths across billions of years, softening a hot, early glow into a faint background only a few degrees above absolute zero. The light kept moving, and the universe changed the light as it went. In that stretching time, becomes part of the signal. The light we detect now is old, not only because it has crossed an immense distance, but because the universe through which it traveled has changed beneath it. Its color has been altered by expansion. Its energy has been diluted. What began as the glow of a hot young cosmos now reaches us as a cold whisper from the beginning of visibility. It is ancient light, but also transformed light, carrying both the past it came from and the history of the space it crossed. This is why the cosmic microwave background is so important to the story. It gives us the first major answer to the question of first light, but it also complicates the question immediately. If we ask for the oldest light we can observe directly, this ancient background is the answer. If we ask for the first starlight, it is not because the universe had become transparent before it had built the stars that would later shine inside it. The first escaped light opened the path, but it did not yet fill that path with stars. The cosmic microwave background is more like the first open window than the first candle beyond it. It shows us that light could finally travel, but it does not show us stars or galaxies. It reveals a universe that had just become clear enough to leave an image of itself before the familiar sources of light had been born. The first escape of light was therefore not the beginning of the night sky. It was the beginning of the universe becoming readable. The image it left is not a picture in the ordinary sense. It has no mountains, no clouds, no suns, and no glowing islands of galaxies. It is a map of tiny temperature variations spread across the sky, differences so small that only careful instruments can measure them. One region is slightly warmer, another slightly cooler, and the pattern is faint, but it is not meaningless. It is the first visible record of a universe that was almost smooth, but not perfectly smooth. Those tiny differences are the same quiet unevenness that mattered inside the opaque universe before. They are the earliest visible traces of the density variations that would later guide structure formation. In the cosmic microwave background, the future is not shown as galaxies yet. It is shown as potential, as slight departures from perfect sameness, as the first visible hint that the universe would not remain smooth forever. The later cosmos is not drawn there in detail, but its first tendencies are present. That is part of its beauty. The first escaped light does not show us a cosmos already filled with things. It shows us a universe just beginning to carry the conditions for things. It is smooth enough to feel almost empty, but not perfectly smooth. And hidden inside those small variations are the paths matter would later follow, into dark matter halos, gas clouds, stars, and galaxies. The background is both an ending and a beginning, the end of the opaque plasma and the beginning of a visible record. Much later, human beings would learn to read this ancient glow, though not at first as a grand portrait of creation. In the 1960s, two radio astronomers, Arno Penzias and Robert Wilson, were working with a sensitive antenna and found a persistent background noise they could not easily remove. It came from every direction. It remained after they checked their equipment, accounted for known sources, and tried to understand why the signal would not disappear. What seemed like an unwanted background became a message from the earliest visible universe. Nearby, other scientists had been thinking about what a hot early universe should have left behind. If the universe had once been dense and hot, then some remnant radiation should still exist, cooled and stretched by expansion. The strange noise in the antenna matched that prediction. A signal that had crossed the universe for billions of years had arrived inside human instruments, almost as an inconvenience. A stubborn background presence that turned out to be one of the most important discoveries in modern cosmology. The oldest light did not announce itself as spectacle. It appeared as something faint, persistent, and impossible to dismiss. There is something quietly fitting about that. The oldest light had been surrounding Earth all along, passing through the sky, day and night, long before anyone had built a machine capable of noticing it. When it finally entered human awareness, it did so as a faint excess, something small enough to be mistaken for an instrumental problem, and large enough to change our picture of the universe. The first escaped light had become a scientific clue waiting inside ordinary noise. Later missions would measure it with far greater precision. Spacecraft such as COB, EUMAP, and Planck mapped the cosmic microwave background across the whole sky, turning that faint radiation into a detailed record of the early universe. Their maps showed extraordinary smoothness, but also the tiny variations that gave structure its beginning. The result was both simple and profound. The universe had once been almost uniform, but not quite. Almost uniform, but not quite, is enough for cosmic history. A slightly denser region could pull on matter a little more strongly. A slight difference in the early distribution of energy and matter could become meaningful once gravity had enough time to work. These were not galaxies yet, and they were not stars, but they were the earliest visible clues to why the universe would eventually become clumpy, textured, and full of form, instead of remaining a perfectly smooth haze. The background did not show the first stars, but it showed why the universe could one day make them. The first escaped light, then, is not only a relic, it is a boundary. When we look at the cosmic microwave background, we are looking back as far as ordinary light can take us, because before that the universe was opaque and photons could not carry a clear image across distance. After that threshold, light could travel, leaving behind a kind of surface from which the visible universe seems to open. Astronomers sometimes call this the surface of last scattering. It is not a solid surface like the surface of a planet or a wall at the edge of space. It is the farthest glowing layer we can see from the time when photons last scattered off free electrons before traveling freely toward us. In every direction we look, if we look far enough, we meet that ancient light. It surrounds us not as a wall, but as a horizon in time. This gives the universe a strange kind of horizon. We are surrounded by the first light that escaped, not because it comes from a shell physically enclosing us, but because looking into distance is also looking into the past. The farther light has traveled, the earlier the time we are seeing. The cosmic microwave background arrives from the age when the universe first became transparent enough to leave a visible record. Beyond it, in ordinary light, the young universe becomes hidden again. Still, the background is not the end of the question. It is tempting to think that once light escaped, the universe entered something like the night sky we know, but the opposite is closer to the truth. After the background glow began its journey, there were still no stars to shine within the newly transparent space. No galaxies had gathered into bright islands, no planets circled suns, and no later kind of starlight had yet appeared. The universe had opened a path for light, but it had not yet built the sources that would fill that path with stars. The glow itself did not remain a warm, visible light bathing the cosmos forever. As the universe expanded, the background cooled and slipped out of ordinary sight. What remained was transparent space filled mostly with simple gas dark matter and the quiet pull of gravity. The first clearing had happened, but the first stellar dawn had not. The universe had become visible in one sense while entering a new kind of darkness in another. This is the strange pause at the center of the early universe. Transparency arrived before illumination. The window opened before there was a landscape full of lamps. The oldest light began crossing space, carrying a record of the universe's infancy, while the matter left behind entered a quieter and colder age. Hydrogen and helium would drift through expanding space. Dark matter would hold invisible patterns of gravity. Slightly denser regions would continue to draw material inward, not quickly, not dramatically, but with the steady patience that belongs to cosmic time. The first light had escaped, and now the universe was about to enter the dark. After the first ancient glow escaped, the universe did not suddenly become a sky. There was transparency now, but almost nothing to shine inside it. The cosmic microwave background began its long journey across space, stretching and cooling. As the universe expanded, while the matter left behind entered a quieter condition. The charged fog had thinned, and light could travel more freely than before, but the familiar sources of light had not yet formed. There were no stars, no galaxies, no planets, no bright islands of matter gathered into shape. The universe had opened a path, but for a long time, that path led through darkness. This period is often called the cosmic dark ages, and the name carries a certain stillness. It does not mean that nothing existed. It means that the universe had become transparent before it had become luminous in the stellar sense. The background glow was still present, but as expansion stretched, it had faded away from visible light into longer and colder wavelengths. What remained was a vast cooling universe, filled mostly with hydrogen-helium dark matter and the quiet influence of gravity. It was simpler than the cosmos we know, but not empty and not inactive. The darkness of this age is easy to misunderstand. It was not the darkness of a room after a lamp has been switched off because there had never been a lamp. It was not the darkness between stars because there were no stars to create such spaces. It was a deeper kind of darkness, a world before visible structure, where matter was present but not yet gathered into the forms that could burn. The universe was no longer blinded by its own brightness, but it had not yet produced the fires that would give distance shape. In that long interval, ordinary matter existed mostly as neutral gas. Hydrogen was by far the most common with helium beside it, and only the faintest traces of other light elements. Heavier elements, such as carbon, oxygen, silicon, and iron, had not yet been made in stars because stars themselves did not yet exist. There was no dust in the familiar astronomical sense, no rocky planets, no metal-rich clouds, no chemistry complex enough to lead toward life. The material of the universe was almost primordial, and because it was so simple, the road toward the first stars was both possible and difficult. Gas does not automatically become a star simply because gravity exists. It must gather, compress heat, and in the right way cool. This can sound contradictory at first because stars are hot objects, but cooling is essential to their birth. A gas cloud collapsing under gravity has to lose some energy in order to keep falling inward instead of resisting collapse with pressure. In the later universe, dust and heavier elements help gas cool efficiently, but in the dark ages, those helpers were absent. The first gas clouds had to find a way to collapse with only hydrogen, helium, and a few simple molecular pathways available. So the universe waited, but it was not waiting passively. Dark matter, invisible to light but powerful through gravity, had already begun to shape the deeper architecture of the cosmos. It did not shine, and it did not collide or cool like ordinary gas, but it gathered under its own gravity into growing regions of attraction. These regions became the hidden wells into which ordinary matter could slowly fall. In a universe without stars, dark matter provided the first scaffolding of structure, not as something seen, but as something followed. The tiny density variations preserved in the cosmic microwave background now began to matter more and more. A region that was only slightly denser than average could pull a little more strongly on nearby matter. Over immense spans of time, that difference could grow as gravity amplified what had once been almost imperceptible. Matter did not gather everywhere equally. It drifted toward the places where the earliest unevenness had given gravity a small advantage, and those places became the first quiet centers of future structure. This movement was slow, but it was not smooth in the simple sense. The universe was expanding, and that expansion stretched the distances between regions, even as gravity worked locally to gather matter together. Ordinary gas responded to pressure, motion, and cooling, while dark matter gathered differently, forming invisible halos that could hold gravitational influence long before they held stars. The Dark Ages were therefore not a blank pause between two brighter chapters. They were an age of preparation, where the visible universe had not yet appeared, but the conditions for visibility were being assembled. There is a strange beauty in imagining that kind of darkness. No star marked a direction. No galaxy outlined a depth. If there had been an observer, there would have been little to see in visible light, only an expanding sea of cold gas and the fading background glow slipping ever farther from human sight. Yet beneath that apparent simplicity, the universe was beginning to organize itself. The first future landscapes were not made of mountains or oceans, but of gravitational preference, of places where matter was becoming more likely to gather than elsewhere. Neutral hydrogen filled much of space, and that hydrogen would become one of the defining substances of this era. It did not shine like a star, but it was not meaningless. It could absorb and emit radiation in particular ways, and much later scientists would search for traces of this dark period through subtle signals from hydrogen itself. The Dark Ages are difficult to observe directly because there were no bright objects lighting them from within. They are known partly through what came before, partly through what came after, and partly through the physical traces that neutral gas may have left across cosmic time. This makes the Dark Ages one of the most mysterious passages in the story of first light. We can see the cosmic microwave background, the ancient glow from before the darkness. We can see galaxies from later times, after stars had begun changing the universe. But the interval between them is harder to read, because the universe was not yet giving us the kinds of luminous markers astronomers usually rely on. It was a time when gravity was writing the next chapter in a nearly invisible script. The word dark can make this period feel like absence, but the better image may be depth. The universe was deepening before it was shining. Matter was falling into wells it could not see. Gas was beginning to collect in regions where the pull of dark matter had made a place for collapse. The first stars were not present yet, but their future homes were being built without light, without noise, and without any obvious sign that fire would one day begin there. As gas fell into these early gravitational wells, it could grow denser. Density brought collisions. Collisions changed temperature and motion. In some places, simple molecules, especially molecular hydrogen, may have helped the gas radiate away energy more effectively, allowing collapse to continue. These details matter because the first stars required a path from diffuse gas to concentrated heat, from wide drifting matter to a center dense enough for nuclear fusion. The Dark Ages were the long crossing of that path. Still, nothing about this process was guaranteed to look like star formation today. Later stars form in environments already enriched by previous generations with heavier elements and dust grains that change how gas fragments and cools. The first stars had no such inheritance. They were being prepared out of almost untouched material inside an early universe whose chemistry was simpler and whose conditions were unlike the star-forming clouds we can observe nearby. This is why the Dark Ages are not merely a gap in the story. They are the setting in which the universe had to invent its first way of making a star. The pace of this invention was cosmic, not human. Millions of years passed. The background radiation cooled further. Gas became colder and more diffuse on large scales, while in denser regions it could be drawn inward by gravity. The universe was becoming less uniform, not because anything was shining yet, but because matter was slowly choosing paths shaped by the earliest variations. Darkness in this sense was not a failure of creation. It was the condition in which structure could grow without yet being seen. There is a calm tension here that is easy to miss if the story moves too quickly toward the first stars. The universe had already crossed one threshold when light escaped from the early plasma, but it had not yet crossed the threshold that would make ordinary cosmic night possible. A night sky requires stars. It requires separate sources of light scattered through space, each one giving distance a pattern. During the Dark Ages, the universe had transparency, without a night sky, openness, without visible landmarks, and time, without any familiar celestial clock. The Dark Ages also force us to think about patience in a physical way. Nothing in this period resembles the dramatic images that often define astronomy. No spiral arms, no star clusters, no glowing nebula, no supernova remnants expanding like bright wounds in space. Instead, there is the slow work of conditions becoming possible. Density grows where gravity has an advantage. Gas drifts inward where dark matter has made a deeper well. Cooling pathways begin to matter. A future star is not yet an object, but a direction in which matter is being carried. This is why the Dark Ages belong at the center of the story rather than at its edge. They remind us that the first light was not a simple sequence from darkness to brightness. The universe first had to become clear, then it had to become dark in a new way, and only then could the first stellar light matter. Without this interval, there would be no slow gathering, no hidden wells of gravity, no primordial clouds collapsing toward their first ignition. The darkness was not an interruption of the story. It was the chamber in which the next kind of light was prepared. As the first dense regions grew, the conditions inside them began to separate from the quieter background around them. Gas drawn into a dark matter halo could become compressed enough for temperature and density to rise. If cooling allowed the collapse to continue, the center could become more concentrated, more unstable, and more capable of transforming gravitational energy into heat. Somewhere in that long process, the universe approached a new kind of threshold, very different from the release of the cosmic microwave background. This time, light would not escape from everywhere at once. It would begin in particular places. Those places were still hidden from direct view in the story we can reconstruct today. We do not have a photograph of the first collapsing cloud or a direct image of the first object that crossed from gas into star. What we have are models, traces, later consequences, and the logic of a universe that did eventually fill itself with light. The Dark Ages therefore end not with a simple visible scene, but with a question forming inside the darkness. How did the first fires ignite in a universe made almost entirely of hydrogen and helium? The answer leads towards stars, unlike any we have seen directly. They were born without the chemical inheritance later stars would receive. They formed in an age when the universe was still young, when the first galaxies had not yet fully gathered, and when every source of light could change the surrounding darkness in ways no star before it had done. From the long dark age, the story now moves toward those first hidden fires, the first stars no one has seen. The first stars arrived out of a darkness that had been preparing them for a very long time. In the hidden wells of dark matter, primordial gas had gathered slowly, pulled inward by gravity, and shaped by the faint unevenness left from the early universe. Hydrogen and helium, almost untouched since the first minutes of cosmic history, drifted into denser regions where collapse could begin. There were no older stars to enrich this gas, no dust grains to help it cool easily, no previous generations to leave behind a familiar path. The universe was trying to make stars for the first time from materials simpler than any star-forming cloud we see around us today. These first stars are usually called population 3 stars, a name that can sound backwards until we understand the history behind it. Astronomers use population 1 for relatively young, metal-rich stars like the Sun, and population 2 for older stars with fewer heavy elements. Population 3 refers to the hypothetical first generation, made almost entirely from hydrogen and helium before stars had manufactured and scattered heavier elements into space. In astronomy, metals means nearly everything heavier than hydrogen and helium, so these first stars were metal-free in that special scientific sense. They belong to a universe before carbon, oxygen, silicon, iron, and the richer chemistry that later generations of stars would inherit. No one has seen one directly, and that is the quiet tension at the heart of this part of the story. The first true stellar lights are central to cosmic dawn, but they remain absent from our images, inferred through models' consequences and the changes they must have caused. We know the universe eventually filled with stars and galaxies, and we know that heavier elements appeared later, which means some first generation had to live, burn, and die before the later universe could become chemically rich. But the first individual stars themselves remain beyond direct observation, hidden behind distance time and the limits of the light that has reached us. This makes them different from the cosmic microwave background. The ancient background glow can be mapped across the sky. It surrounds us as a real signal, faint but measurable, from the moment the universe became transparent. The first stars are more elusive. They are not a visible surface surrounding us, and they did not appear everywhere at once. They formed in particular places inside early gravitational wells, and they may have lived so briefly that by the time galaxies became easier to observe, the first stars were already gone. Their absence does not make them less important. In some ways, it makes them more mysterious. They are like missing witnesses whose testimony survives in the world they changed. Later stars contain elements that had to be forged somewhere. Early galaxies show signs of radiation heating and chemical enrichment that point back toward earlier generations. The intergalactic gas itself carries evidence of having been altered by sources of energetic light. The first stars may not have left us portraits, but they left consequences. To imagine their birth, we have to return to the primordial gas inside the first dark matter halos. Gravity pulled the gas inward, and as it compressed, it heated. For collapse to continue, the gas had to lose energy, but without heavier elements and dust, it could not cool in the ways later gas clouds often do. Molecular hydrogen likely played an important role, allowing some energy to radiate away and helping the cloud continue its inward fall. This was a delicate path because the early universe had only a limited set of tools. Out of that simple material, the first dense stellar cores began to form. The stars that emerged may have been very different from the Sun. Many theoretical models suggest that population 3 stars could have been much more massive, hotter, and brighter than familiar stars, though the exact range remains uncertain. Some may have reached tens or even hundreds of times the mass of the Sun, while other possibilities allow for a wider variety. The point is not that every first star must have been a giant in the same way. The point is that the conditions of the early universe favored a kind of star formation, unlike the star-forming regions enriched by later generations. A massive star lives quickly. The more massive it is, the more intensely it burns through its fuel, and the shorter its lifetime becomes. If many of the first stars were extremely massive, then they may have shone with extraordinary power and disappeared after only a few million years, a brief time on cosmic scales. Their light would have been intense, especially in ultraviolet radiation, the kind energetic enough to affect the hydrogen around them. These were not gentle lanterns placed in a finished sky. They were fierce young engines inside a universe still learning how to become luminous. The word light becomes complicated again here. When we picture the first stars, we may imagine visible points shining against blackness, like the first stars appearing at dusk. But much of their importance may have come from radiation human eyes cannot see. Ultraviolet photons from hot massive stars can ionize hydrogen-stripping electrons from atoms and changing the state of the surrounding gas. In this way, the first stars did not only illuminate nearby space, they began to alter it, preparing one of the great transformations that the wider universe would later undergo. This local quality matters. The first escaped light of the cosmic microwave background came from the whole universe as it became transparent. The first stars brought a different kind of light, born in particular places where gas had collapsed deeply enough to ignite nuclear fusion. The universe was no longer glowing everywhere in the same ancient way. It was beginning to form sources, separate fires, points of energy that could influence their surroundings from within the dark. Inside each first star, gravity and heat pressed matter into a new condition. Hydrogen nuclei fused into helium, releasing energy that pushed outward against the inward pull of gravity. This balance is what allows a star to shine. For the first time, the universe had made objects that could generate their own sustained light, not merely release old radiation from an earlier state. A star is not just glowing matter. It is a furnace held together by gravity, where pressure, temperature, and nuclear fusion create a long, luminous struggle against collapse. In the first generation, that struggle may have been especially short and intense. Massive stars burn hot, and hot stars spend their fuel rapidly. When such stars reach the end of their lives, some may have collapsed into black holes, while others may have exploded in powerful supernovae. These deaths mattered as much as their lives, because a star's end can scatter newly made elements into surrounding space. The early universe, once almost entirely hydrogen and helium, began to receive its first traces of heavier material through stellar death. This is one of the most important changes in cosmic history. Carbon, oxygen, and other heavier elements did not exist in meaningful amounts at the beginning. They had to be made inside stars and released back into space. Without that process, there would be no rocky worlds, no water-bearing planets, no chemistry like the chemistry that later life would require. The first stars, therefore, stand at a strange threshold. They were born from a simple universe, but through their burning and dying, they began making the universe less simple. That does not mean we should imagine the first stars instantly filling space with richness. The change was uneven and slow. One star, or one group of stars, could enrich its local surroundings, while vast regions remained nearly pristine. Explosions could drive gas outward, heat nearby material, and disturb the very clouds from which new stars might form. Light and matter began entering a more complex relationship. The first stars made new possibilities, but they also disrupted the quiet conditions that had allowed them to form. There is a delicate contradiction here. The first stars helped create the future of star formation, but they may also have made it harder for some nearby gas to collapse. Their radiation could heat gas and break apart molecules that helped cooling. Their explosions could scatter material, compress some regions, and empty others. Cosmic dawn was not a smooth spreading of light across a passive universe. It was a turbulent beginning where each new source changed the environment that would produce the next one. Still, from this turbulence came inheritance. Later stars would not be born in exactly the same universe. Even tiny amounts of heavier elements could change how gas cooled, fragmented, and formed new stellar populations. The first generation may have opened the way towards smaller, longer-lived stars, toward richer clouds, and eventually toward galaxies whose light came from many generations at once. The universe was beginning to develop memory, not in a conscious sense, but in the material sense that each generation left conditions for the next. Because the first stars have not been directly seen, the language around them must remain careful. Scientists speak through models and probabilities, not through photographs. They ask how primordial gas cools, how massive the first stars could become, how long they might live, what kinds of supernovae they might produce, and whether any low-mass members of that first generation could have survived until today. The answers are not all settled. That uncertainty is not a weakness in the story. It is part of what makes the first stars feel like a real frontier rather than a completed chapter. There are searches for their traces in the most distant galaxies, in the chemical fingerprints of ancient stars, and in the background, history of hydrogen. A very old star with extremely low metal content can act like a fossil, preserving clues about what earlier explosions contributed to the gas from which it formed. A distant galaxy with unusual light may hint at very young, metal-poor stellar populations. A signal from neutral hydrogen may eventually reveal how the first sources began heating and changing the darkness. Each clue is indirect, but together they help outline the missing generation. The first stars therefore ask us to accept a different kind of seeing. We do not see them as bright points in a telescope image, at least not yet. We see them through the absence. They fill in the logic of cosmic history. We see them through the elements that could not exist without stellar furnaces, through the radiation needed to begin transforming hydrogen, and through the early galaxies that later gathered stars into larger systems. They are invisible in the direct sense, but deeply visible in consequence. For a listener imagining this age, the most important thing may be scale and solitude. A first star would not have risen over a planet or shone above an ocean. There were no eyes beneath it, no atmosphere to color its light, no familiar night to receive it. It burned inside a young universe, still mostly dark, surrounded by primordial gas and invisible gravity. Its light spread into a cosmos that had never known a star before. It did not belong to a sky. It helped create the possibility of one. And then, after burning briefly by cosmic standards, many of these first lights vanished. Some ended in collapse. Some may have exploded with such force that they scattered heavy elements into the surrounding gas. Some may have left black holes that later influenced the growth of early galaxies. Their lives were temporary, but the changes they began were not. The first stars were less like permanent lamps and more like initiations, brief sources that made future complexity possible. As more such stars formed, the darkness was no longer uniform. There were places where light had appeared, places where gas had been heated, places where the first heavy elements had been thrown outward, and places where gravity continued to gather matter into deeper structures. The universe was still young, still mostly simple, and still far from the rich cosmic web we see today. But it had crossed another threshold. Light was no longer only an ancient background glow. It was being made inside stars. From here, the story begins to widen. A single star can change its surroundings, but the universe would not become the cosmos we know through isolated fires alone. Gravity was still gathering matter into larger regions, drawing gas stars and dark matter into early systems where many sources could form together. The first stars did not remain merely individual sparks in the dark. Their light, their deaths, and their chemical remains began to feed the birth of larger, luminous communities. Those communities would become the first galaxies. The first galaxies did not appear as finished cities of stars. They began as gathering places, shaped by gravity long before they became bright enough to resemble anything we would recognize as a galaxy. In the dark matter halos that had grown from tiny early differences, gas collected, cooled, collapsed, and began forming stars and clusters and groups. Some of those stars may have belonged to the first generation made almost entirely of hydrogen and helium. Others formed from gas that had already been touched by the deaths of earlier stars, carrying the first faint traces of chemical inheritance. This is where the story widens from isolated fires into luminous structure. A single first star could change the gas around it, but a galaxy is a deeper kind of transformation. It is a place where gravity holds many processes together: star formation, stellar, death, gas, inflow, chemical, enrichment, radiation, and motion. The universe was no longer only producing scattered lights in the dark. It was beginning to organize light into systems that could grow, merge, and remember their own history through the material they contained. The earliest galaxies were probably small by the standards of the great spiral and elliptical galaxies we see in the later universe. They were not quiet, balanced structures with settled disks and graceful arms. They were young, irregular, and still assembling, drawn together through the merging of smaller halos and the continuing fall of gas. Their shapes would have been restless because the early universe itself was restless. Matter was still finding the first large patterns it could hold. Inside these young systems, the first stars changed the conditions for the next stars. Their radiation heated nearby gas. Their explosions scattered heavier elements into surrounding regions. Their deaths may have left behind black holes or compact remnants that shaped later activity. Each generation altered the material from which the following generation would form, so the early galaxies became places where cosmic memory began to accumulate. A galaxy was not just a container of stars. It was a place where consequences could be gathered and reused. That memory was chemical as much as structural. Hydrogen and helium had dominated the young universe, but stars made new elements in their cores and released some of them when they died. Even a small amount of carbon-oxygen or other heavier elements could change how gas cooled and fragmented. This meant that later stars inside early galaxies might form differently from the very first stars. The universe was beginning to move away from its original simplicity, not everywhere at once, but in pockets where stars had lived and ended. The word galaxy can make this stage feel more mature than it really was. We may imagine a vast, shining island full of billions of stars turning slowly in the dark. But the earliest galaxies were closer to beginnings than to finished islands. They were uneven concentrations of matter, where stars were forming rapidly, where gas was being disturbed and recycled, and where gravity was still drawing smaller pieces together. Their light was real, but their identities were still in motion. This makes them especially important for the story of first light. The first stars may have lit the darkness in particular places, but galaxies allowed light to become more persistent. A galaxy could form many stars, not just one. It could continue pulling in gas. It could survive the deaths of individual stars and use their remains as material for future generations. In this way, light began to have continuity. It was no longer only a brief stellar life appearing and vanishing in isolation. Yet early galaxies were not gentle containers. They were environments of pressure, heat collapse, explosion, and renewal. New stars formed from gas. Then massive stars quickly changed that gas through radiation and winds. Supernovae could throw material outward, stirring the surrounding medium, while gravity could pull some of that material back again. A young galaxy was not merely shining. It was breathing in a cosmic sense, drawing gas inward, heating it, losing some of it, enriching it, and gathering more. This breathing was uneven. In some regions, star formation may have flared intensely, producing many hot young stars in a relatively short time. In others, radiation and explosions may have pushed gas away, slowing the birth of new stars until matter could cool and fall back. The early universe did not build galaxies with a smooth hand. It built them through repeated disturbance, through small mergers, through bursts of formation, and through the constant negotiation between gravity pulling inward and energy pushing outward. The first galaxies also changed the meaning of distance. During the Dark Ages, there was transparency, but little visible structure. With early galaxies, the universe began to acquire landmarks, not in the human sense, but in the physical sense, that light now came from particular regions. A galaxy could send radiation outward from a concentrated place. It could mark a location in cosmic history. It could become an object whose light, if it survived the journey, might one day tell distant observers that structure had begun. But that journey was not simple. These galaxies formed in a universe still filled with neutral hydrogen, and that hydrogen did not allow all kinds of light to pass easily. The same gas that had made the Dark Ages possible now surrounded the first luminous systems. Their starlight could travel through local spaces, but energetic ultraviolet radiation met a medium that it could alter, absorb, and struggle against. The first galaxies, therefore, did not simply shine into an open cosmos. They shone into an environment that still had to be changed. This tension gives early galaxies their place in the larger story. They are not only the next objects after stars. They are the bridge between the first separate fires and the transformation of the wider universe. Inside them, stars are born and die. Around them, gas is heated, enriched, pushed outward, and pulled back in. Beyond them, neutral hydrogen waits, absorbing much of the most energetic radiation. A galaxy is bright, but its brightness is not automatically free. For now, the most important thing is that early galaxies became the places where many earlier threads came together. The tiny density variations from the first escaped light had grown into gravitational structure. Dark matter halos had become the invisible frames around which gas could gather. The first stars had begun making radiation and heavier elements. Now, these elements of the story were no longer separate. They were being bound into systems where the universe could produce light again and again. There is a quiet shift here from event to process. The release of the cosmic microwave background was a threshold that happened everywhere, a broad change in the relationship between radiation and matter. The first stars were local ignitions, the first separate fires in the dark. Early galaxies were something else, ongoing engines of transformation. They did not merely mark a moment when light appeared. They created environments where light could be renewed, multiplied, and organized across time. This is why galaxies matter so deeply in the slow appearance of the first light. Without them, the universe might have had scattered generations of stars, bright but brief, each changing only its local surroundings. With galaxies, gravity could hold the story together. Gas could be gathered into deeper reservoirs. Stars could form in groups and generations. Chemical enrichment could build upon itself. Light could become not just an occurrence, but a continuing feature of cosmic structure. The earliest galaxies were also likely responsible for much of the radiation that would later transform the wider universe. Hot young stars produce ultraviolet light, and in a young galaxy full of massive star formation, that radiation could be intense. Some of it would be absorbed inside the galaxy itself by gas and dust, where dust had begun to exist. Some of it might escape into intergalactic space. The fraction that escaped would matter enormously because it could begin changing the neutral hydrogen beyond the galaxy's boundaries. This brings a new tension into the story. A galaxy can be bright and still hidden. It can produce powerful radiation and still struggle to let that radiation escape. Gas within and around it can absorb light, scatter it, or reshape what finally travels outward. The first galaxies were therefore not simply lamps placed in a transparent room. They were more like fires burning inside walls of gas, gradually finding cracks through which their influence could spread. The early galaxy is therefore not just an object to picture. It is a problem in motion. How much gas does it gather? How quickly does it turn that gas into stars? How many massive stars are formed? How much of their radiation escapes? How much energy from supernovae opens channels through the surrounding medium? And how much gas is blown away before it can form the next generation? These questions matter because the first galaxies did not merely shine. They helped decide how far their light could reach. Modern observations of very distant galaxies give us glimpses of this early stage, but those glimpses arrive transformed by time. Light from the earliest galaxies has traveled for billions of years, stretched by the expansion of the universe into infrared wavelengths. What began as ultraviolet or visible light may reach modern telescopes as something much redder and fainter. To read it, astronomers have to separate signal from distance, age gas, and instrumental limits. The first galaxies are not nearby objects we can inspect easily. They are ancient messages changed by the long journey that made them available to us. Even so, those messages have become richer. Some very distant galaxies appear surprisingly bright for their age, suggesting that star formation gathered strength quickly in at least some regions. Others show signs that heavier elements were already present earlier than a simple expectation might suggest, which means previous stars must already have lived and died. These findings do not turn the story upside down in a sensational way, but they do make the early universe feel more active, more varied, and more capable of rapid growth than a simple picture would allow. That sense of surprise should be handled carefully. The early universe was not breaking its own rules. It was revealing that the rules, when followed through complex conditions, could produce richness sooner in some places than expected. Dense regions collapsed. Gas flowed inward. Stars formed intensely. Explosions enriched their surroundings. Galaxies grew through merging and accretion. What looks startling from our distance may be the natural result of many processes working together in the first few 100 million years. Still, the surprise is narratively valuable because it keeps cosmic dawn alive as a frontier. The first galaxies are not just an old chapter written neatly in the past. They are part of a story still being interpreted through faint signals at the edge of observation. Each new measurement can shift our sense of how quickly stars formed, how early heavy elements appeared, and how much radiation escaped into the surrounding universe. The dawn is ancient, but our reading of it is still young. Within the documentary's larger movement, this section is the turning point from first sources to collective transformation. The universe has now produced not only stars, but places where stars can gather into history. Light is no longer only the ancient background glow, and no longer only the brief life of a first star. It is becoming structured through galaxies, through repeated formation, through the growing complexity of matter held together by gravity. Yet the wider universe is not fully open to that light. Between the young galaxies stretches a vast medium of neutral hydrogen left over from the age after recombination. Around each luminous system, radiation begins pressing into this gas, ionizing some regions and failing in others. The light from early galaxies has power, but it also has work to do. It must carve its way into a universe that still carries the fog of its earlier darkness. So, the story narrows again not to a single star or a single galaxy, but to the boundary around them. Inside, stars are burning, dying, enriching, and being born again. Outside, neutral hydrogen waits, absorbing the most energetic light and hiding much of what the first galaxies are trying to send. The next great transformation begins at that edge where young light meets ancient gas and the first bubbles open in the hydrogen fog. Around the first galaxies, light met resistance. Inside those young systems, stars were forming, burning, dying, and enriching the gas around them. But outside them stretched a much wider universe, still filled with neutral hydrogen. This gas was not opaque in the same way as the early plasma before the cosmic microwave background, when free electrons scattered light everywhere. The fog now was different. It was quieter, colder, and more selective, but it still shaped what early light could do. Neutral hydrogen is simple, but it is not passive. An atom of hydrogen holds one electron around one proton, and if a photon carries enough energy, it can knock that electron loose. This process is called ionization, and it lies at the center of the next great transformation. The first stars and galaxies did not merely send light into space. They sent out radiation energetic enough to change the atoms that filled space. For the youngest galaxies, this meant that light had to do work before it could freely travel. Ultraviolet photons from hot massive stars pressed outward from crowded regions of star formation, moving through gas inside the galaxy, then into the material beyond it. Some were absorbed almost immediately. Some were stopped by dense clouds close to their source. Others escaped farther, carrying enough energy to ionize hydrogen in the surrounding intergalactic medium. Wherever that happened, a small region of changed space began to open. This is the beginning of ionization, but it should not be imagined as a single event washing evenly across the cosmos. It began unevenly around the places where the first strong sources of radiation had formed. A young galaxy could carve out a local bubble of ionized gas around itself, while vast regions farther away remained neutral. The early universe did not become transparent all at once. It became patchy, marked by islands of cleared space, surrounded by a much larger hydrogen fog. The word bubble is only an image, but it is a useful one. It helps us picture a region where light has changed the state of the gas around a source. Inside the bubble, much of the hydrogen has been ionized, meaning electrons have been separated from protons. Outside it, neutral hydrogen still dominates, and the most energetic light has a harder time passing. The boundary between the two is not a perfect shell, but a shifting frontier where radiation gas density and gravity all shape how far the clearing can spread. In the beginning, many of these bubbles would have been small. A single star or a small cluster of stars could ionize its surroundings, but the universe around it was vast and hydrogen was everywhere. If the source died quickly, the bubble might stop growing, and in denser regions, some electrons could recombine with protons again. The clearing of the universe was therefore not a simple outward march. It was a struggle between ionizing light and the tendency of matter to remain or return to a neutral state. This struggle gives ionization its slow drama. The same universe that had once become transparent after recombination was now being changed again, but by a very different process. The first transparency came when the whole cosmos cooled enough for electrons to settle into atoms. This second transformation came when stars and galaxies produced radiation strong enough to tear some of those atoms apart again. The universe had gone from ionized plasma to neutral gas, and now in patches back toward ionized gas. The repetition can sound strange until we notice the difference. The early plasma was hot and dense, and it trapped light because free electrons were everywhere. The later ionized bubbles were thinner, more spread out, and created by local sources. They did not return the universe to its first opaque condition. Instead, they helped clear the way for certain kinds of light to travel across intergalactic space, especially light that would otherwise be absorbed by neutral hydrogen. This is why the first galaxies mattered beyond their own borders. They were not only collections of young stars, they were engines changing the medium between galaxies. Every massive star that burned hot enough, every cluster that released ultraviolet radiation, every burst of star formation that allowed some photons to escape, contributed to the growing patchwork of ionized regions. The light from these galaxies was not just revealing structure, it was helping create the conditions under which structure could later be seen. But the process depended on escape. A galaxy could form many hot stars and still keep much of their ionizing radiation trapped inside its own gas. Dense clouds, turbulent material, and the remnants of star formation could absorb photons before they reached intergalactic space. For ionization to move outward, some radiation had to find paths through the galaxy and beyond it. The early universe may have depended not only on how many stars were born, but on how porous their galaxies became. This makes the first galaxies feel less like simple lamps and more like living, unstable furnaces. Star formation could fill them with radiation, but explosions from massive stars could also punch cavities through gas opening channels where light could escape. At the same time, those explosions could disturb future star formation heat material and throw enriched gas into surrounding regions. A young galaxy was full of competing effects. It produced the light needed to clear the fog, but it also shaped and blocked the paths that light had to take. The local surroundings of a galaxy mattered enormously. A photon leaving a cluster of hot stars might first pass through gas inside the galaxy itself, then through gas that had been blown outward by earlier explosions, then into the wider intergalactic medium. Each layer could absorb, redirect, or allow the photon through. A small difference in density could decide whether radiation died close to its source or helped open a larger clearing. This made ionization not only a question of brightness, but a question of channels, cavities, and escape routes. In some places, bubbles likely grew quickly, around clusters of galaxies or regions where star formation was especially intense. In other places, the fog remained thicker for longer. Cosmic dawn was therefore not one smooth sunrise across all of space. It was more like a landscape of scattered clearings, each one expanding at its own pace, some merging with neighbors, others fading or slowing where sources were weak. The universe became less neutral, not as a uniform sheet, but as a mosaic. The density of the gas mattered as much as the brightness of the sources. A photon traveling into a thin region could go farther before meeting a hydrogen atom. In a denser region, the same kind of photon might be absorbed sooner. Gravity had already made the universe uneven, and that unevenness now shaped the spread of light. The earliest bright regions were often surrounded by complex environments where gas was flowing, collapsing, heating, and being driven outward by the very stars that had formed from it. This gives the hydrogen fog a physical texture. It was not a smooth mist waiting to be lifted. It had knots, filaments, denser pockets, and wider spaces shaped by gravity and expansion. Ionizing radiation moved through that texture, clearing some paths more easily than others. Around the first galaxies, the fog could thin into bubbles, but beyond them, neutral hydrogen still waited in vast stretches, absorbing the most energetic signals and hiding much of the young universe from direct view. For modern astronomers, this patchiness matters because it affects what ancient light can reach us. Some early galaxies may be visible not only because they are bright, but because they formed inside or near ionized regions large enough to let certain light escape. A line of radiation that should have been swallowed by neutral hydrogen might survive if a galaxy has already cleared a bubble around itself. When scientists find such signals from very early times, they are not only seeing a galaxy. They may be seeing evidence that the galaxy has altered its surroundings. This is why the first bubbles are so narratively powerful. They turn light from a symbol into an agent. Light is not only something that arrives at the eye or the telescope, it acts on matter. It separates electrons from protons. It heats gas. It changes what later photons will encounter. In the early universe, light did not merely travel through history. It made history more transparent. Still, the clearing was incomplete. For a long time, most of the space between galaxies may have remained neutral, while pockets around early sources grew and overlapped only gradually. The universe could contain brilliant young galaxies and still be difficult to read across large distances. A source might shine intensely, but if the surrounding hydrogen was thick enough, much of its most revealing radiation would never travel far. Visibility depended not only on the birth of light, but on the changing condition of everything between source and observer. There is a quiet patience in this image of cosmic dawn. One bubble opens around a young galaxy. Another opens somewhere far away. A cluster of early sources pushes a larger clearing into the fog. Between them, neutral regions remain slowly shrinking as more stars form and more radiation escapes. The first light did not conquer the dark in a single wave. It worked locally repeatedly, unevenly, until the separate clearings began to matter on the scale of the whole universe. This stage also links the first stars to the later cosmic web. The same gravity that gathered gas into halos and galaxies had arranged matter into a vast pattern of dense and thin regions. Ionization followed that pattern because light was produced where matter had collapsed, and it traveled differently depending on the gas it met. The first bubbles therefore grew inside a universe already shaped by hidden structure. Light was not spreading through an empty room. It was moving through a textured, evolving medium that had been prepared long before the first stars burned. As more galaxies formed, the number of ionizing sources increased. Generations of massive stars came and went, each one adding radiation heat and chemical change to its surroundings. Some galaxies may have been small, but numerous, contributing many modest clearings. Others may have been brighter, producing larger regions of ionized gas around them. The total transformation came not from one kind of object alone, but from the combined effect of many sources working across immense time. There are still uncertainties in this part of the story. Scientists continue to study which sources contributed most to ionization, how much ionizing radiation escaped from early galaxies, and whether early black holes also played a meaningful role in some regions. The broad picture is clear. The neutral hydrogen fog was gradually ionized by the first luminous structures. But the details remain active because the process was distant, patchy, and difficult to observe directly. This uncertainty should not weaken the story. It gives the dawn its living edge. What matters for the larger journey is the transformation itself. The universe had already become transparent once when the ancient background light escaped. Then it had passed through darkness, formed the first stars, gathered the first galaxies, and begun producing new radiation from within structure. Now that radiation was changing the spaces between structures. The universe was no longer only making light. It was slowly making room for light. At the edges of the bubbles, the next phase was waiting. As separate ionized regions expanded, the distance between them began to shrink. Clearings around galaxies approached other clearings. The hydrogen fog, once spread across enormous stretches of space, became increasingly broken. What had begun as local openings would eventually connect into something larger until the universe crossed another threshold, not simply from darkness to brightness, but from scattered visibility to a cosmos broadly open to the light of stars and galaxies. At first, the clearings were separate. Around one young galaxy, ultraviolet radiation pushed into the hydrogen fog and opened a region where atoms had been ionized. Far away around another cluster of early stars, a second clearing grew inside the same ancient gas. Across the young universe, these regions expanded unevenly, shaped by the brightness of their sources, the density of the surrounding hydrogen, and the hidden architecture of dark matter underneath it all. The universe was no longer uniformly dark in the old sense, but it was not yet transparent in the way it would later become. The next great change happened when those separate regions began to meet. A clearing around one galaxy could grow until it touched another, and then another, joining small local openings into larger, connected spaces. Neutral hydrogen, once spread widely through intergalactic space, became more broken, more patchy, and less able to stop the most energetic light everywhere at once. The cosmos did not pass through this transition like a curtain being lifted smoothly from one side to the other. It changed more like mist, thinning across a wide landscape, denser in some valleys, clearer on some ridges, with openings spreading where the first sources had burned strongly enough. This section is not about the birth of the first bubbles anymore. It is about what happened when those local changes became a cosmic condition. Ionization in its later stage turned scattered visibility into wider visibility. The first transparency allowed ancient radiation to leave the hot young universe. This second transformation allowed the later universe to become readable through the light of objects inside it, stars, galaxies, and eventually quasars shining across enormous distances. By this stage, galaxies were no longer only isolated beginnings. They were becoming more numerous, more active, and more capable of influencing the space between them. Some were small and faint, but there may have been many of them, each contributing a modest amount of ionizing radiation. Others were brighter, with intense star formation, or perhaps early black holes, helping to produce energetic light. The combined effect mattered more than any single source. Across millions upon millions of years, accumulated radiation from early structures steadily changed the intergalactic medium. The intergalactic medium is easy to overlook because it sounds like emptiness. It is the space between galaxies, but it is not nothing. In the early universe, it contained gas left over from the first eras of cosmic history, stretched thin by expansion, but still present across vast scales. During the Dark Ages, much of that gas was neutral hydrogen. During ionization, it became increasingly ionized, and that shift changed what kinds of light could cross the universe without being absorbed. In a neutral universe, certain ultraviolet light from young galaxies could be stopped very effectively. Hydrogen atoms could absorb photons with the right energy, preventing them from traveling far and hiding many of the earliest sources from direct view. In an ionized universe, that obstacle was greatly reduced. Light still had to cross distance, still had to be stretched by expansion, and still could be dimmed or altered by matter along the way. But the great hydrogen fog no longer closed around it in the same way. The universe was becoming transparent, not as an abstract state, but as a physical condition built by generations of stars and galaxies. There is a deep reversal in this. After recombination, electrons joined nuclei, and the universe became transparent because there were fewer free electrons to scatter ancient photons. During reionization, the opposite happened to hydrogen atoms across intergalactic space. Energetic light split many of them apart again. Yet this did not make the universe return to its first blinding plasma. The cosmos had expanded enormously, the gas was far thinner, and the ionized regions created by early sources allowed light from galaxies to travel more freely through the space between them. The same word ionized belonged to two very different cosmic conditions. That distinction is important because it shows how the universe did not simply repeat itself. The early opaque universe was hot, dense, and almost uniform compared with what came later. The Ryanized universe was colder, larger, more structured, and filled with separate sources of radiation. Light was no longer trapped in a universal sea of charged particles. It was moving through a vast web of galaxies, gas, and growing emptiness, crossing regions that earlier generations of stars had helped to clear. As the clearings overlapped, visibility became less local. A young galaxy no longer needed to sit inside a small private opening for some of its light to escape. The cleared regions were becoming part of a wider, connected environment. Radiation could travel farther before meeting neutral hydrogen. Signals from distant objects had a better chance of surviving the journey through intergalactic space, though that journey would still stretch them into longer wavelengths and weaken them almost beyond recognition. The universe was becoming readable across scale. This did not mean that all darkness disappeared. Even after reionization, space remained vast and mostly empty by human standards, with galaxies separated by immense distances. Darkness in the ordinary visual sense still filled the intervals between stars and galaxies. What changed was not that the cosmos became bright everywhere. What changed was that light from luminous structures could cross those intervals more freely, carrying information from one region to another, and eventually to observers who would arise much later. In this sense, the universe became visible, not by becoming uniformly illuminated, but by becoming transparent enough for contrast. A galaxy can only be seen as a galaxy if its light can leave it and remain distinct from what lies around it. A star can only mark a place if photons from it can cross space without being erased immediately by the medium. Visibility depends on separation source and distance, light and background, object and observer. Ryanization helped create the large-scale conditions in which those separations could matter. Scientists study this transition partly through the light of very distant quasars and galaxies. A quasar powered by a supermassive black hole at the center of a young galaxy can shine so brightly that its light passes through huge stretches of intergalactic gas before reaching us. Along the way, neutral hydrogen leaves marks by absorbing particular wavelengths. When astronomers examine that light, they are not only studying the quasar itself, they are also reading the state of the gas between the quasar and Earth, using distant brightness as a lamp shining through ancient fog. Those observations suggest that by the time the universe was roughly its first billion years old, rayonization was largely complete, though the exact timing and pace remain subjects of careful study. The ending is easier to outline than the beginning, because once the intergalactic medium is mostly ionized, the signs become clearer in the light of distant objects. The earliest stages are harder hidden in a time when sources were faint bubbles were small, and neutral hydrogen was still common. Ryanization was not a single date on a cosmic calendar. It was an extended transformation whose details changed from place to place. That uncertainty gives this part of the story its quiet edge. Astronomers still ask which sources were most responsible. Were countless faint galaxies the main agents, each contributing a little light until their combined effect reshaped the universe? Did brighter galaxies dominate in some regions? Did early black holes add important radiation, or were young stars enough? The broad movement is accepted, but the balance of causes remains an active question, and each new observation of the early universe can shift how that balance is understood. The truth is more patient than a simple summary. The first galaxies did not merely clear the fog and finish the work. Some regions became transparent earlier than others. Some galaxies may have sat inside large ionized regions, while others remained hidden behind neutral gas. Some sources may have contributed strongly for brief periods, while many smaller galaxies may have done the quieter work, of transforming the wider medium over time. Cosmic dawn was not one sunrise, but a sky slowly opening in different places at different times. Imagine the universe as a vast, darkening field where small clearings appear far apart. At first, each clearing belongs to its own source, a young galaxy or cluster of stars burning in a local hollow of changed gas. Then the clearings widen, their edges soften, and some begin to touch. The spaces between them shrink. Eventually, what had been isolated openings becomes a connected expanse, and the fog that once defined the whole field survives only in smaller remnants. The image is imperfect because cosmic reionization was not a visible mist moving through ordinary air, but it helps preserve the feeling of the process. The universe did not switch from hidden to revealed. It became revealed by degrees. The end of reionization also changed the future of observation. Once the intergalactic medium was mostly ionized, the light from galaxies could travel across the cosmos with fewer interruptions from neutral hydrogen. Later generations of stars and galaxies would shine into a universe more open than the one their ancestors had entered. The first luminous structures had not only appeared within space, they had altered space for those that came after them. Visibility itself became an inheritance built by sources that would never be seen in the familiar night skies of later worlds. The universe that emerged after reionization was still young, still changing, and still far from the mature cosmos we see nearby. Galaxies would continue to grow, collide, form stars, build heavier elements, and shape the cosmic web across billions of years. But one of the essential barriers had been crossed. Light from stars and galaxies could now move through intergalactic space in a way that made large-scale cosmic history visible. The cosmos had become a place where luminous objects could leave records beyond their own neighborhoods. This is the deeper meaning of the section's title. The universe becomes visible not because every place is bright and not because darkness disappears. It becomes visible because light can carry memory across distance. A galaxy can announce that it exists. A quasar can illuminate the gas between itself and us. A faint signal can leave an early source survive the changing universe and arrive billions of years later as evidence. Visibility is not just brightness. It is the survival of information. And yet this transformation did not leave a simple picture behind. The farther back we try to look, the more difficult the reading becomes. The earliest galaxies are faint, their light stretched into infrared by cosmic expansion. The gas around them may hide or reshape the signals we most want to understand. The first stars remain unseen directly. The timing of reionization is reconstructed through scattered clues, through background radiation, quasar spectra galaxy surveys, and careful models of how light and hydrogen must have interacted. That is where the story begins to turn toward us. The universe became visible long before there were eyes to see it, but its first visible chapters did not vanish completely. Their light kept traveling. Their effects remained in the state of intergalactic gas. Their chemistry entered later generations of stars. Their faint signals crossed almost the entire age of the cosmos, waiting for instruments sensitive enough to receive them. By the end of reionization, the first great work of light had been done. Radiation had escaped. The early plasma stars had ignited after darkness, galaxies had gathered, and their energy had changed the hydrogen between them. The universe was no longer only a place where light existed. It was a place where light could travel from structure to structure, from ancient sources into the future, carrying the evidence of how visibility itself had been made. The next part of the story belongs to that evidence. Billions of years later, on a small planet around an ordinary star, minds would build instruments to catch the stretched remains of cosmic dawn. They would look into darkness and find that it was not empty, but layered with old signals. The first light had slowly made the universe visible. Now, from very far away in time, we would begin learning how to read it. The universe became visible long before anything existed that could understand visibility. Light crossed the widening spaces between galaxies, carrying traces of stars, gas, black holes, heavy elements, and the long clearing of hydrogen fog. For billions of years, these signals moved through an expanding cosmos, stretched into longer wavelengths, weakened by distance, and altered by everything they passed. They did not know they were evidence. They simply traveled quietly, preserving pieces of a dawn no eye had witnessed. Much later, around one ordinary star in one ordinary galaxy, a small planet formed from material that earlier generations of stars had made possible. On that planet, life eventually learned to look upward, and then to build instruments that could look beyond what eyes alone could see. The story of first light became in its final chapter a story of reading. Reading ancient radiation, reading spectra, reading faint smudges of galaxy, light reading absence where hydrogen had swallowed a signal. The universe had become visible, but understanding what it revealed required patience. Mathematics mirrors detectors and a willingness to listen to light that had almost faded into silence. The first great message was the cosmic microwave background. It came not from stars, but from the earlier threshold when the universe first became transparent and released its ancient glow. To map it was to see a kind of baby picture of the cosmos, not in the sentimental sense, but in the physical sense of a record from a time before galaxies had formed. Its smoothness showed how uniform the early universe had been, and its tiny variations showed why that uniformity would not last forever. In those faint differences, scientists found the seeds of later structure, the quiet beginnings of the galaxies whose light would one day clear the hydrogen fog. But the cosmic microwave background could not show the first stars directly. It marked the opening of the path, not the fires that later formed along it. To reach those fires, astronomers had to look for something much harder, the dim, stretched light of early galaxies, traveling from a time when the universe was only a few 100 million years old. This meant looking not only farther away, but farther back in time, because in astronomy, distance and history are bound together. The deeper a telescope looks, the older the light it receives. That old light is not the same when it arrives as when it left. As the universe expands, the wavelengths of traveling, photons are stretched, shifting light toward the red end of the spectrum, and for the earliest galaxies, often into infrared. A young galaxy may have emitted ultraviolet or visible light, but by the time that light reaches us, it can arrive in wavelengths human eyes cannot see. The dawn of stars, therefore, becomes visible to modern instruments, not as a golden sunrise, but as faint infrared signals gathered by cold mirrors and sensitive detectors. To see the first galaxies, we do not simply look harder. We look in the right kind of light. This is where telescopes become part of the story without becoming the whole story. Hubble gave humanity some of its deepest views of galaxies across cosmic time, revealing a universe crowded with distant structure. It showed that even small patches of dark sky could contain thousands of galaxies when observed long enough. But for the earliest galaxies, whose light had been stretched beyond visible wavelengths, a different kind of instrument was needed. Webb was built to see deeply in infrared, to catch the light of objects so distant that expansion has moved their signals out of ordinary sight. When Webb looks toward cosmic dawn, it is not seeing the first stars as individual stars. That remains beyond our reach for now. Instead, it sees early galaxies, clustered light from many stars, gas, and perhaps other energetic sources, all compressed by distance into faint shapes and spectra. A tiny red object in an image may represent a galaxy whose light began traveling when the universe was still young enough for ionization to be incomplete. It may be a clue not only to what stars existed there, but to how much gas surrounded them, what elements were already present, and whether their radiation had begun to clear a local opening in the hydrogen fog. The image alone is never enough. A distant red smudge may look ancient, but color by itself can mislead because dust distance and other effects can imitate one another. To know how far away a galaxy truly is, astronomers turn to spectroscopy. They spread the light into its wavelengths, looking for features that reveal redshift composition, temperature, and ionized gas. In a spectrum, a faint galaxy becomes less like a dot and more like a message with grammar breaks, lines, absences, and signatures that can be read. This act of reading is one of the quiet marvels of modern astronomy. A few photons gathered after a journey of more than 13 billion years can tell us that hydrogen was present, that oxygen may already have been forged, that stars had lived and died before the light we see was emitted. A line shifted far into the infrared can tell us that space itself has expanded enormously since the signal began. The absence of certain light can speak as clearly as its presence, because missing wavelengths may reveal what intervening hydrogen absorbed. In this way, cosmic dawn is reconstructed, not from a single picture, but from a layered interpretation of what light kept lost and became. Some of Webb's early findings have made the young universe feel more active than many simple expectations suggested. Very distant galaxies have appeared surprisingly bright, and in some cases, they show signs of development star formation or chemical enrichment earlier than one might casually imagine. This does not mean that the Big Bang has been overturned or that the basic story has collapsed. The calmer and more accurate truth is more interesting. The early universe was capable of building luminous structure quickly in some places, and our observations are forcing scientists to refine how that happened. That refinement matters because cosmic dawn was never a uniform process. Some regions grew faster because their matter gathered earlier or more efficiently. Some galaxies may have formed stars intensely, while others remained faint. Some may have allowed ionizing radiation to escape into the surrounding gas, while others trapped much of it inside. Webb's discoveries do not replace the story of cooling collapse, first stars galaxies, and reionization. They add texture to it, showing that the dawn was not only slow, but uneven rich, and still partly hidden behind the limits of what we can measure. The most distant galaxies also carry the tension of ancestry. If a galaxy seen only a few 100 million years after the Big Bang already contains heavier elements, then stars must have formed, lived, and died before that galaxy's light began its journey to us. We are not seeing the absolute first moment of light, but a scene that already has a past. Even at the edge of observation, the universe is not offering a clean beginning. It gives us traces of earlier unseen events, reminding us that cosmic dawn recedes as we approach it, always leaving another layer just behind the one we can detect. This is why the first stars remain so haunting. They are necessary to the story, but not yet directly visible as individual objects. We infer them from the chemistry of later gas, from the need for ionizing radiation, from the formation of early galaxies, and from models of primordial star formation. They may have been massive, hot, short-lived, and powerful, but their exact properties remain uncertain. The documentary began with light trapped in a universe too bright to see, And it ends with another kind of hiddenness, not opacity, but distance, faintness, and the fact that some first sources may have vanished before leaving direct portraits. Even so, the search continues in many forms. Astronomers look for unusually metal-poor stars in our own galaxy, hoping they preserve chemical fingerprints from the first stellar explosions. They study distant galaxies whose light may contain hints of very young, primitive stellar populations. They search for signs of how neutral hydrogen changed over time, trying to map the slow progress of reionization. Each clue belongs to a different layer of evidence, and none alone gives the whole dawn, but together they begin to outline the age when darkness first filled with sources. There is also something humbling about the scale of delay. The light we receive from an early galaxy left before Earth existed, before the Sun existed, before the Milky Way had taken its familiar form. It crossed a universe still growing and changing, while generations of stars formed and died elsewhere, while heavy elements accumulated, while planets eventually gathered from the debris of earlier stars. By the time the signal entered a telescope near Earth, the galaxy that emitted it may have changed beyond recognition, merged with others, or disappeared into a larger structure. Astronomy is always looking at what was not what is. That delay is not a weakness. It is what makes astronomy a form of time travel, though not the kind that can change the past. We receive ancient light in the present and use it to reconstruct conditions that no longer exist in the same form. The universe becomes an archive written in photons, and every distant signal is both a location and an era. To read cosmic dawn is to accept that the beginning is not nearby, not simple, and not waiting in one place. It is spread across signals of different ages, each carrying a partial memory. The work is delicate because early light rarely arrives cleanly. It has been stretched by expansion, weakened by distance, filtered by gas, and blended with the light of many stars inside distant galaxies. Astronomers have to ask whether a faint red object is truly ancient, whether its spectrum confirms its distance, whether a bright signal comes from stars' hot gas or an active black hole, and whether the surrounding hydrogen has allowed the light to escape. Every claim about cosmic dawn has to pass through this patience. The farther back we look, the more carefully we have to distinguish wonder from certainty. This is one reason Webb has changed the emotional texture of the early universe. It does not simply give us prettier pictures. It makes the boundary between the known and unknown feel closer. A galaxy once too faint to confirm may become a measured redshift. A hint of chemical enrichment may become a clue that earlier stars already lived and died. A signal that should have been absorbed may suggest that a galaxy had carved a clearing around itself. Each observation is small compared with the age of the universe, but together they make the dawn less abstract and more alive. The story of first light then has no single final image. There is the smooth ancient glow of the cosmic microwave background. There are the invisible first stars known through what they must have changed. There are the earliest galaxies, faint and red, whose light has been stretched almost beyond recognition. There is the hydrogen fog not seen directly like a cloud in daylight, but inferred through the way it absorbs hides and releases signals across time. Each piece is real, but none alone is the whole dawn. This is why the phrase, "the first light in the universe," becomes richer by the end than it was at the beginning. It can mean the radiation that escaped when the universe first became transparent. It can mean the first stars igniting after the dark ages. It can mean the first galaxies gathering enough luminous power to reshape their surroundings. It can mean the ionizing light that cleared openings in neutral hydrogen, or the stretched infrared glow now caught by telescopes looking back toward cosmic dawn. The phrase does not point to one candle. It points to a sequence of thresholds. For a long time, the universe had to change before light could carry meaning. First, matter had to stop scattering photons so completely. Then gravity had to gather gas into the first hidden wells. Then stars had to form from simple primordial material. Then galaxies had to hold many sources together. Then their radiation had to open paths through hydrogen until visibility became a large-scale condition rather than a local exception. The first light appeared slowly because the universe itself had to become capable of being read. And now reading continues. Every new deep observation is not just a farther look into space, but a question sent into the early dark. How quickly did the first galaxies grow? How massive were the first stars? How much ionizing radiation escaped? Which sources cleared the fog? And how unevenly did that clearing unfold? These questions do not disturb the calm of the story. They keep it alive because the dawn is not less beautiful when it remains partly unknown. In the end, we are not standing at the first sunrise. We are standing very far away from it in time and space, gathering what survived the journey. The light is faint now. It has been stretched, cooled, filtered, and thinned almost to nothing. But it still carries structure, memory, and consequence. It still tells us that the universe was once opaque, then transparent, then dark, then slowly lit from within. The first light did not arrive all at once. It escaped, faded, waited, ignited, gathered, cleared, and traveled. It crossed billions of years to become a signal in our instruments and a question in the human mind. And when we look toward the deepest dark, we are not looking into emptiness. We are reading the remains of a dawn so old that even now, after all this time, it is still arriving. The first dawn of the universe was not a single moment. It was a threshold crossed slowly, almost too slowly to imagine. Light existed before there were stars, but it could not yet move freely. Later, it escaped as an ancient glow. Later still, after a long darkness, the first stars and galaxies began to make the universe visible in another way. What makes this story beautiful is not only that light appeared, but that space itself changed enough to carry it. Across billions of years, that early light has continued to travel. It reaches us, altered, stretched, softened by time, but still carrying the memory of a universe becoming transparent, becoming structured, becoming visible. And perhaps that is why the first light feels less like an event than a quiet unfolding. The universe did not simply turn on, it slowly became readable. And even now, as our telescopes look farther into the dark, we are still learning how to recognize the dawn.